Good afternoon. Okay, the last time we finally found the state function that we need in order to predict if a reaction goes by itself, is spontaneous, or if it's not spontaneous. And the state function was the Gibbs free energy. And we defined this with that little zero in the exponent as Gibbs free energy at standard conditions. And we have seen that there's a relation between the Gibbs free energy and the enthalpy and the entropy. And we can determine these Gibbs free energies at specific temperatures. So you calculate the Gibbs free energy from the enthalpy at this temperature, the change in enthalpy at this temperature, and the change in entropy at that temperature. So with this, we have the change in free energy at standard conditions is delta H at standard conditions, the change in enthalpy at standard conditions, minus the temperature multiplied with the change in entropy at standard condition, okay? And we know if this is smaller than zero, then we have a spontaneous reaction. The reaction goes in the direction that we have calculated, all right, or have written the reaction. If it is equal to zero, then we have it in equilibrium. So the universe doesn't care if you have products or reactants. Products and reactants are in perfect equilibrium with each other, and we're going to talk about this today. So in order to calculate the change in free energy, and we omit the word Gibbs, the change in free energy at standard conditions is the sum of the change in free energy of the formation of the products, the free energy of formation of the product, minus the change in free energy of the formation of the reactants. And you can calculate those. They are given in tables. And with this, you see if that number is now smaller than zero, as I said, then it will be a spontaneous process. And we have looked briefly at the free energies, and obviously when you make CO2, they're all negative. The free energies of formation of those guys here, CO2, water, liquid water, gaseous water, magnesium oxide solid, and ethanol, they're all negative. So they all form these compounds from its individual products. So you also have a look, please, at we have solid carbon. The entropy is given in joule per Kelvin per mole, joule per Kelvin per mole. And you see the entropy is an absolute number. It's 6 for solid carbon. For graphite, it's 6. It's a very low number, pretty ordered solid. When would we have entropy 0? Who said that? Who said never? That's absolutely right. Never. Exactly. We never have entropy 0 because we could have entropy 0 if we would be able to make a perfect crystal and keep that crystal at absolute 0 temperature. But we cannot reach absolute 0 temperature, and with this was a very good answer. And with this we are unable to have an entropy of 0, as we are unable to reach the absolute 0 point of temperature. So, but the absolute number is 6 is pretty good. It's pretty small. Compare another solid is 33, or magnesium oxide is even a little bit more ordered than magnesium itself. And if you go now from the solid to the liquid, let's look at liquid water is 70, and there's no other liquid in there. Yeah, there's alcohol, it's 161. It's a little different, of course. It's a larger molecule. And then you go to the gas, so the entropy should increase even further, and you do that. Steam is 189, CO2 gas is 214, oxygen is 205, and hydrogen gas is 131. So we go from order to disorder. And this is reflected in these numbers. There's one trick here, or one stone that you can stumble over. This is in joules, okay? but you have your temperature in Kelvin, so you multiply this with that, the delta with this, you get a very large number in joules. But the rest of this is in kilojoules. This and this is in kilojoules. You have to recalculate this into kilojoules, okay? You have to consider that factor 1,000. Then we played a little bit at different conditions, if H is exothermic or endothermic, and endotropic or exotropic conditions. That means we looked at different temperatures, and then at the end we did some reaction. It was a little bit fun. Of course, we used the reactions where delta G was negative. Sometimes we had to go in the opposite direction in order for it to be negative, because in the direction as the reaction, for example, aluminum bromide will not spontaneously form aluminum and bromine liquid, and this was a delta G at the room temperature of positive delta G. That means we had to do this reverse. We used aluminum and bromine liquid, and then we fired it up and it became aluminum bromide. You know, it was an exothermic reaction. So we played with this, and today there is nothing. Today is Friday. So let's warm up a little bit, and let's see where you are, if you got the hang of all this. And let's have a little chem quiz. We have the reaction CO2 and calcium oxide. This is a gas and this is a solid. Forms a solid that is called calcium carbonate. And we have delta H, not of this reaction, is about minus 200 kilojoules per mole. And delta S, not, so this is at standard conditions, is minus 200 joules per mole Kelvin. Now I'm asking you, for which temperature range is the reaction spontaneous? If, this is in Kelvin, of course, because we're talking about Kelvin here. Is it smaller than 1,000 degrees Kelvin? If the temperature is smaller than 1,000 degrees, would it be spontaneous? Or at 1,000 degrees, or larger than 1,000 degrees? Why don't you think about it? Your equation is right here, okay? Why don't you think about it and give me your answer? You don't have to really use your calculator. Use your brain. That's the best calculator you have. Cheap too. No, actually it costs food. Okay, let's get with it. Everybody got the answer, or are you still using your TI 5 million? Everybody needs to have this right. Let's see what your thinking is. Yes, good. Now, there's a couple of people, there's 64 people who need a bit of an explanation. I really don't care today. Anyhow, isn't that what they are saying? Okay, because everybody can calculate that, all right? We say delta G is delta H, okay? Delta H is minus 200 kilojoules per mole. And then let's just say 1,000 degrees. Let's put 1,000 degrees in there. So 1,000 times 200, this would be this here. This would be minus times minus, this would be plus. So this is negative and this would be plus. So 200 times 1,000 is 200,000 joules per mole per Kelvin, but we need it and we multiply with Kelvin, so this goes away. So we have joules per mole, 200,000 joules per mole. This is 200 kilojoules per mole, okay? So now we have 200 kilojoules here, and you have minus 200, you have minus 200 and you have plus 200 kilojoules, delta G would be 0. At 1,000 degrees, actually it would be in equilibrium at the 1,000 degrees. So in order to make this negative, you have to be smaller than 1,000 degrees, that you don't subtract that from here, okay? That you get negative. And so there is the solution, and this was, of course, A. So this at 1,000 degrees, T times delta S is about delta H. It's not about, actually. It is delta H naught. And larger than 1,000 degrees and smaller than 1,000 degrees, delta G naught is larger than 0. And with this case, it would be smaller than 0. And this was the answer. Okay? Good. Let's do something else now. Today we're going to talk about equilibrium. And we already got an inkling about this. Equilibrium is if delta G is 0. So we have reactants and you have products, and they're all in equilibrium with each other. The universe doesn't care if this is reactants or a product. So it goes back and forth and back and forth. That's what it does. So equilibrium actually, let's see how exciting equilibrium will be today. We say we have A moles of substance A, and we add B moles of substance B. These are our reactants. And we let them react with each other to form C moles of substance C and D moles of substance D. So these are our products, and these are the reactants. So really, in equilibrium, this goes back and forth and back and forth and back and forth. Equilibrium is dynamic. It's not static. Of course, as we look at it, then it's static. There's nothing happening. Let's watch equilibrium, okay? I have a volume of Beijing air here. LA, you were more familiar with LA air, okay? This is NO2, okay? There's NO2 in there, so this comes from the exhaust, obviously. There's NO2, but there's also N2O4. Remember, NO2 can dimerize from these dimers. That was a chem quiz. So it's an equilibrium in N2O4. NO2 is brown, N2O4 is colorless. So there is some colorless gas in there, and the brown is with the colorless in equilibrium, and it goes back and forth and back and forth and back and forth, and the universe doesn't care if it's products or reactants. And macroscopically, this is very exciting. We watch equilibrium. Exciting, isn't it? No, exciting is only when we didn't have equilibrium, because then we could blow something up. We went from reactants to products. They got into equilibrium, essentially, but this would be equilibrium, and this is not very exciting. That's why we don't do a whole lot of equilibrium reactions. We try to get to the equilibrium as fast as we can sometimes, and then you will have a big exothermic reaction, for example. So, but what you need to understand, nanoscopically, that means on a molecular level, you have reactants and you have products. Constantly you form products, and constantly you revert back to reactants. And there's a perfect equilibrium, because the universe allows it, because delta G is 0. The universe doesn't care if you're reactants or product. Okay, it goes back and forth and back and forth. But macroscopically, nothing is happening. All right. So we go back and forth and back and forth, and we're going to look at some of the equilibrium, for example. You have had an equilibrium. That's just the water equilibrium. Liquid water goes to gaseous water. This is an equilibrium. At 100 degrees Celsius, the partial pressure on top of that water that is boiling is 1 atmosphere. And it goes into the solution and comes out of the solution to follow to that condition at 1 atmosphere. That's a perfect equilibrium. For you, just say, oh, water boils, okay? You didn't know that was an equilibrium, all right? And so this would be 1 atmosphere at 25 degrees, and if it boils, What would that be? No, at 100 degrees. I'm sorry, at 100 degrees. What would that be at 25 degrees, like room temperature? Anybody remember? Was the number I gave you? 0.03 atmospheres. It's at 25 degrees, you have equilibrium too. It's the partial pressure on top is 0.03 atmospheres. So that would be a phase change equilibrium. And there are many kinds of equilibrium, and let's talk about a couple of those. There is our equilibrium where we use the partial pressures here. That's the NO2 and N2O4. So this is a gas. This is a liquid-gas equilibrium. This is a gas-gas equilibrium that goes back and forth and back and forth and back and forth. Only in equilibrium once you have determined that delta G naught equals 0. Okay? If delta G naught is larger than 0, nothing goes. If delta G naught is smaller than 0, it goes in this direction. Okay? Once it has equilibrated, then delta G naught is 0. I'm sorry. Delta G naught is 0 for both of them. I'm killing these people here. And is 0 for both of them. Okay? And it goes back and forth and back and forth. All right? So next equilibrium. There's an aqueous equilibrium. We have a little flask here, and we have a concentration. So we have acetic acid. This is an acid equilibrium, the dissociation of acid. And we will talk about this in one of the next lectures. So this is acetic acid, and this transfers a proton to the water here to make H3O+, and then you have acetate there. And this is an equilibrium once delta G equals 0. So this is an aqueous equilibrium. Let's see what other equilibrium we have. A heterogeneous equilibrium. Heterogeneous means we have two different kind of states, two different phases actually. The one is a liquid phase, silver ion and chloride ions. Silver chloride is an equilibrium with silver chloride solid. Didn't you do an experiment in the lab, something like this, solubility of silver chloride? So you have visited the silver chloride equilibrium. So this is an equilibrium, can be an equilibrium. That's the equilibrium equation at least. So now, I know that some of you are struggling with the standard condition thing, okay? Standard condition. Standard condition is a hypothetical state. We said if we have concentrations, everything is at 1 mole. If we have gases, everything is at 1 atmosphere. And this is what we use to calculate if the delta G is negative, 0, or larger than 0, and we use that standard state. But have you ever seen a reaction where you have 1 mole here and 1 mole there, 1 mole of reactants, 1 mole of product? Never happens. You can start out with 1 mole, but then it goes into equilibrium, and it will distribute itself until it has the equilibrium concentrations. So this is not equilibrium, and we talk about standard conditions because you also heard about standard temperature and pressure. Standard temperature and pressure is 1 atmosphere and 0 degrees Celsius. But standard condition is usually you either state the temperature or it's usually at 25 or 293.15, 25 degrees Celsius or 298.15 Kelvin, okay? And so this is standard condition. Standard condition, everything, if it's liquid, at 1 mole. If it's gas, everything at 1 atmosphere. It is not equilibrium at all, far from being equilibrium. And this is something you need to take home, like so many other things. Or bring it to the bank, don't take it home. So let's look at the law of mass action. So here we have our products, and they form reactants. So we can make a reaction quotient. We say the quotient of that reaction is the concentration of this here. So that's the concentration of the product divided by the concentration of the reactants. There's nothing wrong. That's our definition of reaction quotient. You know, what would it be if this would be all gases? What would be Q at standard conditions be? Yes, say it. Say it. It's right what you think. What would it be? Standard condition is 1 atmosphere. Left side, right side. What would Q be? 1. Exactly, it would be 1. And if it would be in concentrations, what would it be? Also 1. Okay? So now we can write this here. These are the concentrations of our products is C times the stoichiometric factor to the power times the concentration of D with the stoichiometric factor to the power of D. Okay? If you have 5 moles here, you have to write 5 here. If you have 2 moles here, you have to write 2 here. Divided by the reactants, you have the concentration of A to the power of A, so that's the stoichiometric number, the concentration of B divided to the number of moles of B, to the power of the number of moles of B. All right? So when we have equilibrium, then we call this quotient equilibrium constant. When we have equilibrium. And this quotient is equilibrium constant, and we call it K. K at a given temperature is at equilibrium. That's the reaction quotient. It can be at any time, totally out of equilibrium, that reaction. Yeah? We have the concentrations of all the 4 reactants, and we put them in, and if it doesn't get to K, then it's not in equilibrium. All right? And so you can look these up here, equilibrium constants, you can look them up in tables for all kinds of reactions. They have been measured. And so you know now I have these products and these reactants, and I know this here, and I know what will happen if this goes to here, or this goes to here, till it reaches that number. So let's make an exercise about this here. What is if Q is smaller than the equilibrium constant? Q is smaller than the equilibrium constant. That means if it's smaller than the equilibrium constant, what does that mean? What do we have too much? We have too many reactants, okay? Too many reactants. So we have to make, Q is smaller? Q is smaller than the equilibrium constant. We have to go to product, okay? We have to make product. And if Q is larger than the equilibrium constant, so that means here, that would be this here, this would be too large, the numerator would be too large. That means we have to go in this direction, we have to make more reactants. So this will tell you, if you have the Q and the K, in which direction you go. We have to make more reactants. So that way you get that concentration down, this concentration will increase till you get to that constant. And that constant is a constant at each given temperature. How can you say it's a constant? I thought it's a constant, then it's a constant. No, the constant is dependent on the temperature, okay? So this is a very allowable situation to say that it's a constant. And in equilibrium, we have Q, that's the reaction quotient, equals K. That's all there is. So you see, once this has reached, you know that you have equilibrium. So let's look at an equilibrium at an example. We have water boiling. And water boils at 100 degrees Celsius, or 373.15 Kelvin. And so the liquid goes into is in equilibrium with the gas phase. So let's write the quotient. So we take that concentration. What would that be? It's a gas. What would we have to put in there? It's a gas. So we can't put, what would be the concentration of a gas? That would be some pressure, wouldn't it be? Yeah. Would be the partial pressure of water above the solution. So that would be the partial pressure of water above the solution. Now we divide this by water, H2O water. That's how we defined our quotient. Reactants divided by product. But we know that pure phases, there's water in water. It's a pure phase. Pure phases you set as 1. P is 1, or you set it as concentration is 1. Okay? Pure phases are set as 1. So you divide this by 1, and then you have, this is your reaction quotient. And with this, the partial pressure is, of course, the vaporization pressure at that temperature above your liquid. So what would be the pressure at 100 degrees? What pressure would that be? Come on, 1. And what would it be at 25 degrees? 0.03, exactly. You're fantastic, phenomenal, how you know all this. Good. So that would be an equilibrium. And with this, in equilibrium, Q equals K. And you can look up what that K is, all right? So we remember when we did this, we had this vaporization pressure here, when we had the P times V is a constant for ideal gases and non-ideal gases or real gases. We had this was the vaporization pressure. And so it was 0.03 at 25 degrees Celsius. And so if you look at this, the pressure and temperature, this is obviously here the curve for the equilibrium. At each temperature here, the liquid and the gas is in equilibrium at this curve, each temperature. See that? Okay? So this, if I want to have the vaporization pressure at that temperature, I go from, put the temperature, look at the temperature, go up to that curve, go across here, and get the equilibrium vaporization pressure at that temperature, or vapor pressure at the temperature. So now I can do the opposite. I can define this how I want it, but we defined it, its products goes to reactants. Now if I write this way, I say this would be my reactant, and this would be my, this would be my product, and this would be my reactant. I could define a new Q, okay? What would that new Q be? One over P. So this is, I say this here divided by this here would be 1 over P. Okay, 1 is this here, we set this as 1. And this is 1 over the vapor pressure at that temperature. Okay, I hope you get the hang of this. And at equilibrium, of course, the partial pressure is the vapor pressure. And this is a different K then because it's 1 over this here. Okay, we call this K prime. So if you look at equilibria and you give an equilibrium constant, it's very important that you also look at the reaction, what the equilibrium constant is, how the equilibrium constant is defined. You always have to look at the reaction because you take the right side divided by the left side is your constant. So let's see if you get to understand here. We have water is obviously boiling here. It goes from liquid to gas, so there is obviously a vapor pressure on top of it, which is true under standard condition. Remember standard condition? I defined this for you, okay? Which is true under standard condition. Is Q smaller than K? Is Q equals K? Or is Q larger than K? Why don't you think about this and give me your answer, please? So first you have to ask yourself, what are standard conditions? We know in terms of concentration, we know in terms of pressure, and I mentioned earlier the temperature, okay? And this is not standard temperature, all right? Alrighty. So some of you say this is equilibrium, because if Q equals K, that would be equilibrium, okay? Some of you say Q is smaller than K. And some of you say Q is larger than K. Why don't we sort of define what standard conditions are? What is standard condition? Standard pressure at a standard reaction, standard condition reaction? What's the pressure? 1 atmosphere. And what's the temperature? 25 Celsius, okay? So you have water at 25 degrees Celsius, 1 atmosphere of pressure above it. You think this is an equilibrium? Okay, but 298.15 Kelvin. Yes. The point, we have 1 atmosphere. This is standard condition. That's not equilibrium condition. All right? The question was, no, I thought it was 0.03 at 25 degrees. That's already the answer, actually. So it's standard condition, okay? Standard condition is 1 atmosphere and 298.15 Kelvin. So you have 1 atmosphere at 25 degrees above water. You ever seen that before? Water boiling at 25 degrees? I haven't seen that before. Yes, I have. You have to reduce the pressure. When you reduce the pressure, then it happens. But we have pressure at 1 atmosphere, okay? Okay, now I confused you completely. And now let's give it another, no. Let's give it another stab here and have a discussion about this, please, and see what you can come up with. You really need to discuss this. Standard conditions are definitely not equilibrium. We established this much earlier, okay? So what is it? Nope. Hmm? Mm-hmm. Mm-hmm. Oh. Exactly. Okay, I'm having my private discussion here. Okay, let's go with C, huh? Let's go with C. Okay, what is the partial pressure? I mean, I told you, what is the, at equilibrium, what's the partial pressure at 25 degrees of water? 0.003, okay? What is Q at 25 degrees? 1. Okay, so 1 is obviously a lot larger than 0.03, all right? So the point is, you have the 1 atmosphere there, and in order to get back to equilibrium, the water has to condense in order to get to 0.03 atmospheres. The 1 atmosphere has to condense into water. You have to make more of the reactant, essentially, to get into equilibrium. So you will get the hang of it soon, I hope. So let's think, there's the solution, okay? So this is Q is the partial pressure of hydrogen. In equilibrium, it's the vapor pressure at that temperature, and this would 25 degrees Celsius. So this is standard conditions. Q would be 1, okay? And at K would be 0.03 at 25 degrees. So Q is larger then K, answer was C. Now let's see if since you're doing so well, how does K vary with temperature? So K varies with temperature, so this would be the phase diagram of water, and this would be increasing the temperature, but I have P here, and I don't have K here, and I would like to plot K here versus T. So how does the equilibrium constant vary with temperature? Does it stay the same? Does it go down, get smaller, or does it get larger with temperature? So why don't you think about this and give me your answer? When I click. Yes! Okay, good. Now, why is that? Now, you've seen here now let me go back here. I showed you that here, and this is obviously the equilibrium of the between the liquid and the gas. So this is the partial pressure of the water at that temperature. I look at the temperature, it's this here, okay? And with this, K is the partial pressure itself. So you can substitute this as K here, and you put K in here, and you put this here, and so it increases with temperature. You see that? As you increase the temperature, the equilibrium constant increases. At each temperature is a fixed value, but it increases with temperature. So this is exactly this curve here, and with this is your answer. All right, good. Now now this would be a landscape of free energy. Let's say that's free energy. There are free energy hill and free energy valley, and this would be not a stable situation. We would be in free energy hill here, so we could roll down here or roll down to here. So this is unstable. With this one, we would really have reached a minimum, and there we would be then in equilibrium. So here we would be also here in a pseudo-equilibrium, but it's not equilibrium because we didn't reach the lowest free energy state. And so this will eventually have to go to here, and this is probably kinetically hindered. So let's just look at this one. So we were unstable, and now we are free energy stable. So the free energy was smaller than zero. It went in this direction, and now we have a stable state, and we are now in equilibrium, okay? And so this was, for example, what we did with the balloon. We exploded hydrogen and water. We reacted hydrogen and water. So the hydrogen and the oxygen, we didn't explode hydrogen and water. We exploded hydrogen and oxygen. We mixed hydrogen and oxygen and reacted with each other. And the reaction products were obviously in a higher free energy state than the reactant. Otherwise, it wouldn't have happened. It wouldn't be delta G negative. And we then reacted it. What happened here? It's not there, okay? And made water, okay? And so this is now the lowest free energy state, and we essentially were in equilibrium. So there are several kinds of equilibria, and we want to look at some of them here. We see this would be, for example, if I plot here the reaction time, all right? That would be as the reaction proceeds, and I plot here the concentration. So you would have a reaction that monotonically, you have the products here, and it goes, and then it comes in equilibrium, all right? So then the concentration doesn't change anymore, and this was what the reaction we just discussed, essentially. We could also have a reaction like a clock reaction, where are we ready? We have a clock reaction where we have here, first it doesn't do anything, and suddenly it goes up, and it goes into equilibrium, and then doesn't change anything anymore. Let's do one of those reactions. I need 3 volunteers, please. 1, 2, 3, right there, the 3 of you. Their hands were up so fast, I couldn't even count fast enough. Okay. There you go. So you stand over here facing the audience, and you will, each of you, do a reaction, an equilibrium reaction, which is a clock reaction. So have a look at your colleagues, please. And what you do, watch me here. You get 2 beakers. Please watch me, okay? You get 2 beakers. It's important. Go a little closer. You have 2 beakers, and you take, each of them has liquid. You pour this quickly in here. That's empty. You pour it back in here. You pour it back in here. And then you hold that one up like you have a toast with each other, next to each other, like a Scandinavian drinking toast or whatever, okay? And or whatever country you want to, okay? And so let's do that then. That's one. Careful here. Don't mix until I say. Okay, you do this here, and you do this here. Now let's mix it in. Oh, don't do that to yourself. Okay. Okay. Go. One. Full in, full back. Full back, and one more time. Done. Okay, done. All right. So hold it up here. Now let's see that. Oh, bam! Did you see it? Well, wait, hold it up there. There it goes. Okay. Let's see that one. There it goes. So this was a clock reaction. It was longer going unreacted than reacted, than was going further. Thank you very much. Don't put it down. Don't hurt yourself. Are you okay? Did you spill something on yourself? No, huh? Okay, good. Thank you very much. So let's have a look at this clock reaction. And so the first one, it went to a certain time, and then it started reacting very quickly. So see, it goes ping, and then it's in equilibrium. The next one went to here, went up, and in equilibrium. And the last one went all the way to here, and then up in equilibrium. Okay? That was a clock reaction. We can do that. There's also reactions which sort of overshoot the equilibrium, and then undershoot it, and then overshoot it again, and then they undershoot it. And this would be an oscillatory reaction. The equilibrium is essentially here, so it overshoots it first, undershoots, overshoots, undershoots, and the frequency becomes, it goes faster and faster until it's in equilibrium, yeah? And so let's do one of those. And let's have a look at this here, please. Let's make it nice and big, that we can see it well. Maybe the light, you can't see it. The light, switch light off. Yeah, there it is, blue. Blue, and so it overshot it. Now it's going to undershoot it. And gold. And blue. And overshot it again. Go Bears. And gold again, undershoot, overshoot. Okay, this goes on and on for a little while until it's in equilibrium, and this will have the color in between, since blue is much denser and darker, so it will be all looking blue, okay? As long as there's no red in there, okay? All right, this was a reaction like this. Like this, we overshot. There was blue, and then gold, blue, gold, blue, gold, blue, gold, blue, gold, till it is in equilibrium. Now there's another reaction to reach equilibrium, which is a chaotic reaction. You probably like those. They are so chaotic that one cannot mathematically predict how it's over and undershoots. Okay, it just goes wild, and then over undershoot, and then total undershoot, total overshoot, and then it goes at the end. It goes into equilibrium. This is called the chaotic reaction. There's no mathematical prediction. So let's see what else we got here. Let's talk about another equilibrium. That's a solid-gas equilibrium. So the solid goes to gas. Okay? What do you call this? What? Sublimation. Okay? Where have you seen this before, sublimation? Here in this class. Carbon dioxide. Solid carbon dioxide went to gaseous carbon dioxide. So we have iodine in here, and okay, and you see this light blue tinge here? See that? This is the iodine, that's solid iodine, and that's the gas, the iodine gas, the I2, yeah, okay? And so now I'm asking you, this is the equilibrium. What happens to the vapor color intensity if I add some more of this iodine? Let's keep that down here, please. What happens to the vapor color intensity when iodine is added? Does the vapor color intensity increase, stay the same, or decreases? Why don't you answer this quickly? Quickly, I give you 1 minute. 45 seconds. You either know it or you don't. Everybody in? Everybody in? Come on, we got to get doing with this. Get going. Okay, it increases. Makes sense, doesn't it? Why don't we do the experiment? All right, let's do the experiment. Stay around. It will be interesting. We do the experiment. I put some more iodine in there, and you have a very close look. I put a whole load of this in there, yeah? So, now watch the color and give me your answer. So I give you 1 minute. We have, 1 minute. It's a short minute. Oh. You see anything? Look at the color sort of above, not directly above. Look at the color. You see anything? I hope so. Hope so. Let's see. Some of you said, he put a whole load of this in there. Got to increase. There's more stuff in there. Color got to increase. The other guy said, I don't see anything here. I don't see nothing. There's nothing going on. And the other guys say, the one, this 11%, they say, he always asks so difficult questions. Maybe I go with the opposite. So let's say decrease, okay? So what really happens is, actually, B is right. It stays the same. And why is that? It's just the vapor pressure of the amount of solid doesn't play any role, because K equals the partial pressure of the iodine, and the vapor pressure, that's the vapor pressure of the iodine. At 25 degrees, it's always the same, and that's independent of the solid. okay? Independent of the solid. So you put 1 there for the solid. Okay, I see you on Monday.